Hey folks, today's topic is end behavior polynomial functions. The idea here is we're trying to talk about what's happening to our graph as x goes towards positive infinity or as x goes towards negative infinity. What's happening at the extreme ends of our graphs. That's what I mean by end behavior. And today we're only looking at polynomials. Polynomials are equations that don't have any roots or x's on the bottom or anything weird, kind of what you would call your traditional equations. So you'll be successful today if by the end of today's notes you can look at a function and then describe its end behavior. In other words, say what's happening as x goes towards positive or negative infinity. So let's start off by looking at an equation and trying to come up with what each term contributes to the overall value of the equation. So if I've already done this, I've already typed this into my calculator, and it turns out that if I put 72 in for all of these x's, this would give me a number that is it is 2,246,984,992. So overall, this number, when you put 72 into this function, you'll get this value. And what I want to talk about is what does each term contribute to that total? So if we look at this 100,000, which is clearly the biggest number out of all of these, this contributes 100,000 to that number. So even though this is the biggest number, this really doesn't contribute that much. I mean, this is a huge number, but in comparison to the overall answer, it really has a small impact. So let's go through, and I want to show you what each term is worth. This next term, when I put 72 in for x, this would be worth 720,000. Next piece would be worth 5,184,000. The 100x cubed contributes 37,324,800. 10x to the fourth, that piece contributes 268,738,560. So what is that last term? What is the x to the fifth? The one that looks kind of like the smallest piece of the puzzle. It actually contributes by far the most to the overall answer. And if you'll see, this turns out to be can never find the good colors. I'm so picky about my colors. This turns out to be 1,934,917,632. So the point of this, what I'm trying to point out, is this term out front dominates so much of this number. This was worth 2.2 trillion, and 1.9 trillion of it came from this value. So these numbers obviously are going to affect the overall total, but they don't affect it nearly as much as this first term. And this first term we call the leading term. Now we're going to come back to that leading term in a minute. This is a leading term. This is a leading term. This is a leading term. We're going to come back to that in a minute, but what I want you to do now is grab your calculator or open up Desmos, and I want you to graph each one of these 8 functions on your calculator and make a real rough sketch. Like I'll do the first one with you. I'm going to use, I'm just going to zoom 6, give me a standard window. I don't really care the details on this. I just need this thing to look close. Okay, so close enough. My graph looks something like that. Good enough. Okay, that's all I need you to do. So go through, pause it, practice typing this into your calculator. I know it seems a little bit like busy work, but we don't type enough into our calc. So I want you to take the time to practice. So pause and give it a whirl. Okay, your picture should have looked something like this. What we want to talk about is the end behavior. And the way mathematicians say that, so this is what your graph should look like. I kind of covered up that last one there. So the way mathematicians talk about this is we talk about it in terms of this thing called a limit. The limit of f of x as x approaches negative infinity, and the limit of f of x as x approaches positive infinity. So let's talk about this notation. Limit means what is happening. So in your head, you can kind of translate it this way. What is happening to my y values? F of x stands for our y values. What is happening to my y values as x goes towards the negatives? Because we're talking about the end behavior, well, there's two ends to our graph. There's the positive end and the negative end. So this describes what's happening as we go towards the negative axis. And then the other limit notation discusses what happens as we go towards the positive axis. So what is happening then? What is happening to my function as x goes towards the negatives? As x goes towards the negatives, which way does my graph go? Down. So what I'm doing is I'm moving along. This tells me which direction to look. Then I answer with what direction the graph goes. So as x goes towards the negatives, my function goes downward. So we would say that this heads towards negative infinity. As x goes towards the positive, my function goes upward, goes towards the positives as well. And then if you'll notice, these two graphs do the same thing. And we're going to talk about what characteristics and why these look the same and these look the same and these look the same. But let's go through and do our limit notation. Our end behavior. Written in limit notation might be a better way to say that. Okay, so that's what we call limit notation. This is read the limit of f of x as x goes towards the negatives, or as x approaches negative infinity. So as x goes towards negative infinity, my y values go up, up, up. I like to put the plus in front. You don't have to. You can just write infinity, but I like to write the plus to remind myself that sometimes I have to write a negative. As x goes towards positive infinity, my function values go down, 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 down. So that's negative infinity. You try the next two. So hit pause, try to write up your limit notation, and try it on your own. All right, let's see. So as x goes towards the negatives, my graph goes up, 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 up. So that'd be positive infinity. As x goes towards the positives, my graph goes up, 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 up. So these are both positive infinity. As x goes towards negative infinity, my graph goes downward on both sides. So that's negative infinity. As x goes towards the positives, my graph also goes down again, so that's negative infinity as well. All right, so what's the big takeaway? We want to be able to do this without our calculator. We want to be able to discuss the end behavior without our calculator. So what I want you to do is I want you to look at these two terms. And I want you to compare them to these two terms, these two functions. And try to see if you can figure out what characteristics do these have versus these two, and then these two versus these two, and see if you can come up with the pattern. Well, all right, let's see what you figured out. If you'll notice, in both of these scenarios, when it comes to the leading term, and yet again, we only care about the leading term, what do you notice about the exponents on both of those? Odd, odd, odd. What are these exponents? Even, even, even. So to help us figure out which way our graph is going to look, one of the characteristics is to look at its exponent. In this case, the exponent is odd. In this case, the exponent is odd. For these two, the exponents are even. Now notice, I'm talking only about the leading term again. And remember, the reason we only care about the leading term is because if I go back to this example, this ending value, which is our function value or our y value, is dominated so much by the term out front that if we want to discuss the end behavior, not if we want to find the actual answer, but if we want to discuss the end behavior, all we have to do is look at the first term. So when our exponent is odd, it kind of makes sense because these are positives. What's a positive to an odd number? Positive. What are negatives to an odd number? Negative. Makes sense. But why are these down here when x to an odd turns out to go the opposite way? My positives now point down and my negatives now point up. That's because of this thing out front called the leading coefficient. My leading coefficient in this case is positive. In this case, my leading coefficient is negative. So I can tell something about I can make a decent sketch of my graph just knowing the exponent and the leading coefficient of the leading term. So in this case, positive squared, positive to an odd goes up, negative to an odd goes down, and then when you multiply by another positive, it's still going to be positive. These are positives. What's a positive 5 times? Still positive, but then we're multiplying it by a negative. That's why this side of the branch falls down. These are negative x's. What's a negative to the 5th power? Negative, but we're multiplying it by another negative, which actually makes it end up being positive. Same thing here. What's a negative 7 times? Negative, but we times it by another negative, which ends up being positive. What is a positive 7 times? Positive, but then we multiply by a negative, which makes it fall downhill. And then the same kind of argument, but talking about even exponents. What's a positive and even number of times? Still positive. What's a negative and even number of times? Still positive. That's why both of these ends point up. But our leading coefficient still plays a role when the leading coefficient is negative. So here, these are positives. What's a positive to the 4th power? It's positive, but then we attach the negative too, and that's what makes that side drop down. These are negatives. What's a negative to the 4th power? Positive, but we times by a negative, which makes that side drop down. All right, so that's a lot of stuff. Let's try to organize this into a simpler picture. So these are the 4 different scenarios. You can have a degree that's odd with a leading coefficient that's negative, or you could have a degree that's odd with a leading coefficient that's positive. Degree even, negative coefficient, positive coefficient. So we're going to look at each scenario. What I want to do first and what I recommend is to just sketch it. Make a little sketch and see what the graph's going to look like. I always start with the positive side because positives want to go positive. So these are positive x's. I have to attach the exponent first. So what's a positive an odd number of times? Positive. But what are we multiplying by? A negative. So that means this side of the branch of the graph is going to fall down. Now, maybe it doesn't look exactly like this, but it's going to be pretty darn close. Okay, what are these? These are negatives, negative x. So let's put a negative x in here. What's a negative an odd number of times? Still negative. But our coefficient is negative, so we're taking this negative answer and we're multiplying it by another negative. A negative times a negative makes a positive. So now I can use this picture. I know it's not perfect, but it's a decent picture. It's enough to help me figure out what my end behavior should be. So what's happening to my graph as x goes negative? As x goes negative, my graph goes up, so this should be positive infinity. As x goes positive, my graph goes down, so this should be negative infinity. Okay, if you feel like you got it, maybe pause here and try to just complete this square or this rectangle. All right, let's see how you did. Okay, so my exponent is odd, but my coefficient is positive. So positives an odd number of times are positive times another positive is still positive. These are negative x's. A negative an odd number of times is going to be negative times a positive. A negative times a positive is still negative. So your graph should look something like this. As I go negative, my graph goes negative. As I go positive, my graph goes positive. All right, at this point, everybody should be able to do the rest of this. Now try to do, let's just do one at a time though. Pause and try to do this one. So this, we've got an even exponent, but we've got a negative coefficient. So these are positive x's. A positive and even number of times is still positive, but we're timesing it by a negative. So this side is going to go downward. These are negatives, and negative an even number of times is going to be a negative, let's say 4 times, would turn out to be a positive, but we're multiplying by a negative, so this one's going to go downward, which means both of our ends are going to be headed towards the negatives. I guess I didn't say this, but just to be clear, the reason we have to do this before we have to do this, exponents are tougher than multiply. Remember, the leading coefficient is the number that's connected by mult, and the exponent is connected by exponents. We have to do exponents first. Pause if you haven't done it yet and do this one. Okay, these are positives. An even number of times is positive times another positive is positive. Negatives, an even number of times is positive times another positive is positive. So now both ends are going up towards positive infinity. All right. Hopefully that makes more sense now that we've sort of graphed on the front. We used our calc to help us figure out some patterns, and now we've kind of organized those patterns into a chart that we can use. So let's use this chart now to figure out the actual end behavior. So I want to make a sketch here. I want to get an idea of what this graph looks like. So here's how I do it. I always start with the positives. A positive 8 times is positive times a negative would be negative. Then I take the negatives. A negative 8 times would be positive, but we're timesing by a negative, so that would end up being negative. So now I know both branches are headed downward, so I can discuss the limit as x approaches positive and negative infinity. And I know it's kind of annoying to write this every time. I don't know what to tell you. Dig deep. All right, so as x goes towards the negatives, my graph goes towards the negatives. As x goes towards the positives, my graph goes towards the negatives. Oh boy, what color should I use to box it in? Green or red? I guess we're going with green. Make a sketch. Pause it if you're feeling pretty confident. Positives. Cubed. Still positive. Times another positive. Still positive. Negatives. Cubed. Still negative. Times a 4. Still negative. There's my branches. limit of f of x. As x approaches negative infinity, limit of f of x as x approaches positive infinity. So as x goes towards the negatives, my graph goes towards the negatives. As x goes towards the positive, my graph goes towards the positives. Well, pause it if you haven't yet. Try to do the next two. Let's see how you did. Make a sketch. Positives to the fourth power are positive. Times a 3 are still positive. Negatives to the fourth power are positive. Times a 3 are still positive. Our limit of f of x as x approaches negative infinity. Our limit of f of x as x approaches positive infinity. Excuse me. The hiccups all of a sudden. X goes negative, my graph goes up. X goes positive, my graph goes up. And last but not least, all right, positives to the fifth are positives, but we're timesing by a negative. Negatives to the fifth are negative, but we're timesing by another negative. That makes it positive. So as x goes towards the negatives, my graph goes up. As x goes towards the positives, my graph goes down. As you can see here, the next little part, let's save that for tomorrow. We'll do that as our warm-up. Hopefully you can do it without having to look back, but you know, this is something you're going to have to memorize at some point. You won't be able to put this on a cheat sheet. All right, gang, good luck.